I explained it to him though. I was like, Lachlan's injured. I'm ready to take his place.
Curve sketching.
Yeah,
Which course you say, why? There's computers that can sketch curves, and you've got that Desmos thing you keep bringing out, and it's really great. And that. And that's true, but some of the problems with using technology to graph are the window that you look at can affect the shape so that it flattens out little valleys, right? Like little local minimums that you don't see because you've got your scale set to such a point where something that does this just looks like this. Okay? So using calculus, we find everything that's out there, right? The curve must yield all of its secrets to us. So we get all the local mins, the local maxes, right? That way the bridge doesn't fall down or the probe does not miss Mars.
Isn't there a button for that?
So the probe missed Mars because one group was working in imperial and one group was working in SI units, and so really, I thought we were using SI. It's like that's the US for you, right? I mean, everybody else in the world, it's all SI. So. Anyways, let us sketch. So we're going to do two examples. Just two. It's painful enough. Two is enough. Trust me. It's like pulling teeth. So, there's only 12 questions, and only 12 because they don't. They take a while to do, right? There's only 12 questions in the book, and so I've chosen two that are sort of representative. As far as sketching polynomial functions, like x to the fifth minus 2x to the fourth, but those are almost trivial, right? So I'm not doing an example of one of those. You can do those. You already know kind of what they look like, right? But what you need to see sometimes is, it's like you're drawing a cubic. We all know what cubics look like. They look like that, he says, sketching a cubic out in the air for the benefit of those not watching. But this will tell you where that local minimum is and where that local maximum is, right? That's what we're going to do now with this. This is not, however, just a plain old cubic, right? Okay, so following the book, the first thing we're going to do is find the domain, right? So the domain is the set of all x such that x squared minus 1 is not equal to 0, which is the set of all x such that x squared is not equal to, that x is not equal to plus or minus 1, or stated in a nicer way, state that in a nicer way down here. Okay. So negative infinity to negative 1, negative 1 to 1, and 1 to infinity, all round brackets or parentheses indicating does not include that, right? So we don't have negative 1, we don't have positive 1. Okay, next step, intercepts. D. What I like to do first is find the y-intercept, because you just put x as 0 in, that's pretty easy, right? I mean, there's not much work to that. So y-intercept, set x equal to 0, gives us 0, 0, right? Which means we also now have the x-intercept. Okay? There are no other x-intercepts, right? So if you're doing a polynomial function, then finding intercepts, you've got methods from last semester that you can use to find those, right, or last year. Symmetry. I always find it and then I never use it when I sketch, but if you actually bothered to use it, if it's even symmetry, you only need to sketch from 0 to the right and then reflect that, right? And you'll have the thing. And if it's odd symmetry, again, you only need to sketch from 0 to the right and then do a dual reflection or a rotation of 180 degrees around the origin. Okay? Okay, so what do we do for symmetry? We figure out f of negative x, right? we just substitute in. Everywhere we see an x, we put a negative x. And we get 2x squared over x squared minus 1, which is the original function, right? Which is equal to f of x. And so we have even symmetry. And the curve is symmetric about the y-axis. Curve is symmetric about the y-axis. Okay, so we've got so this tells me that, you know what, why don't you just sketch from 0 to the right and then reflect that and be done with it, okay? Asymptotes. Again, so like I'll hand this thing out to you, which also has a way of sketching curves, and all forms of sketching curves are going to have some, you know, some variation of what I'm showing you. And the way I'm showing you is just what the book uses: A, B, C, D, E, F, G, H, right? Those steps. Okay, so let's start with a horizontal asymptote. Limit x approaches plus or minus infinity of 2x squared now let's cut to the chase, right? We're going to divide everything by x squared, so it's 2 over 1 minus 1 over x squared, right? Which is, and now you throw it in, so that's 2 over 1, which is 2. Okay, so the horizontal asymptote, y equals 2, right? So we want to sketch that in, right? Next up is the vertical asymptotes, right? Okay, well, those occur when x is equal to plus or minus 1, right? So that's why we do the domain, right? And, you know, you kind of factor it and cancel it down just because maybe there's a point discontinuity, so you want to know that's not an asymptote. You're not going to do that here, but you'll note that there's a point discontinuity here, so you can sketch that in. Or vertical asymptotes, which is what we've got here. So now we got to do 4 things, right? We got to do -1 from the left, -1 from the right, +1 from below and above, however you like to say it. So the limit as x approaches 1 from above of 2x squared over x squared minus 1 is equal to infinity. Right? I mean, that's going to be bigger than 1, but small and positive. And the limit as x approaches, let's do -1 from above. Or maybe we should go this way and do the limit as x approaches 1 from below. It's going to be negative infinity, right? Because this is going to be smaller. Not much, you know, smaller than 1, and when you subtract 1, you'll end up with a very small negative, and that's 2. And you get negative infinity. And -1 from above. That's going to be negative infinity. And -1 from below. 1 there from below. Is going to be positive infinity. So at this point, we can actually do some sketching, right? So I'm going to just I'm going to squeeze in there just a sort of a rough sketch of it. And this is what we did a few days ago even, right? Was we drew a little sketch to say, hey, it looks like this. Because at this point, you know, what can you sketch in? You can just sort of say, well, okay. Right? So we've got our 3 asymptotes going on, right? And we know that as we approach 1 from above, it goes up. Okay? And we know that this goes out this way. As we approach 1 from below, it goes down. As we approach -1 from below, it goes up. Okay, so then, and then this goes this way. And as we approach -1 from below, from -1 from above, sorry, it goes like this. Okay, so we sort of got, and actually probably these do this, right? I mean, what else is there to do? And then there's something going on here, we got to figure out the rest of it. Okay, but that's sort of where we're at now, just with the asymptotes, right? Sketching that in. So just keep that in mind, because you know we're going to take this and then do some stuff with it. Okay, so let's go back. So now comes the fun stuff, right? So E, intervals of increase and decrease. So for that, we need the first derivative, which is fun, right? Because it's a quotient. Well, the first one's not bad. So it's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared, right? Which is equal to, so when you expand this, you're going to get like, what do we got here? We're going to get 4x cubed minus 4x minus 4x cubed, so the 4x cubes go bye-bye, and we just have a negative 4x over x squared minus 1 squared. Okay, so that's just cutting to the chase. If you want to do more work, that's fine, right? You can do another line or two. So always do the amount of work that you're comfortable with, right? And enough to get the correct answer. So you should know yourself well enough to know I got to show a few lines, or I'm going to make a mistake, or I can do this stuff. I'm fairly confident. All right, so intervals of increase. Well, when f prime of x is greater than 0, we have increase. What can we say about the denominator? It's always going to be positive, right? We're squaring it, so something squared is positive. So then we got this negative 4x. Well, that'll be positive when x is negative, and it'll be negative when x is positive. So life is easy on this one, right? So what are we going to say? F prime of x is greater than 0 when x is less than 0. But it can't be -1, right? So any value less than 0, good, but not -1. And f prime of x is less than 0 when x is greater than 0, but it can't be 1. Okay, so it's greater than 0 or increasing. Okay, so let's just do this. So f is increasing from -infinity to -1 and -1 to 0. Okay, so those are intervals of increase. And it's decreasing from 0 to 1 and 1 to infinity, right? Because we're not allowed to have -1 or +1. Right? Those are our asymptotes. So those are your intervals of increase and decrease, right? So it's going up. Going up, which, if we went back here, it's going up. It's going down. Okay. Critical numbers. Okay, so the critical numbers. So the critical number is when this is equal to 0, which is when x is equal to 0, right? So critical number is x equals 0. You don't worry about that. It's just always a positive value. So critical number, x equals 0. Since f prime changes from positive to negative, so positive to negative, at 0, you want to, what's this strange symbol? It's just showing a positive slope going to a negative slope. At 0, what do we have? It goes kind of like this, right? Take that out. So it changes from positive to negative at 0. So the first derivative test says you have a local maximum. Okay, you have a local maximum. F at 0 is a local maximum. By the first derivative test, that's it, by the first derivative test. You can also use the second derivative, right? Remember the second derivative test? You can use that, but in a sense, we don't need to because we've already figured it out, but you could verify it with that. We want the second derivative so we'll know about the concavity, right? It's concave up, concave down. We need to know the shape at those, in those intervals. So, speaking of which, we need the second derivative. So, give me a moment, and then we'll move on and do the second derivative, which is, of course, much more fun than the first. Ready? Looks like. Okay. G, second derivative. Okay, so it's the denominator, which is x squared minus 1 squared, times the derivative of the numerator. And the numerator was minus 4x, right? So that's minus 4. Minus, but seeing as we're going to go minus a negative, right? So we're going to go plus 4x, okay? Because we're doing minus negative 4x, right? So I'm changing that to plus 4x times 2 times x squared minus 1 to the 1, right? That's the derivative of the outer function times the derivative of the inner function, which is 2x, all over x squared minus 1 squared squared, or x squared minus 1 to the 4th. Okay, and now we get to simplify this. So remember, here's what's going to happen generally when you do this, right? Remember, the original denominator was x squared minus 1 squared, and we're going to multiply that 2 out, so we're going to have an x squared minus 1 in common, right? We also have in common a 4 and a 4, right? So we're going to take a 4 out, and we're going to take an x squared minus 1 out. Okay, so let's do that. So I'm going to get a 4 and an x squared minus 1, and that leaves me here with a negative, and then still one of these, so a negative x squared minus 1. And then here, okay, so the 4 is out, so we've got 2, 2, and an xx, so that'll be plus 4x squared. I said that as if there was going to be more, but there isn't. Plus 4x squared. Over. And then these guys here, right, it's always going to reduce. So you're always going to be taking out a factor, which is one of these guys that was down here, so there's always going to be some reduction. So what shall we do? Let's do 2 more steps. Okay, and again, right, the amount of work you do is what you're comfortable with. Like if you want to take this and just do it all and go negative x squared plus 4x squared is 3x squared plus 1. Okay, so it's 4 and then 4 times that. Where am I going? So I'm going to go to 12x squared plus 4 over x squared minus 1 cubed. Okay. So now what we want to know is, when is the second derivative positive, which says concave up? When is it negative, which says concave down? So we take a look at this and we say, I got 12x squared plus 4. Whatever x I put in there, that'll be positive, then I add 4 to it. So 12x squared plus 4 is always positive, right? So that's what we're going to do. Let's see if we can squeeze this in here. So since 12x squared plus 4 is greater than 0 for all x, then what we want to know is, well, let's say this. So f double prime of x is greater than 0 means that x squared minus 1 is greater than 0. Which means that x squared has to be bigger than 1, and a fancy way of saying that is that the absolute value of x is greater than 1. Okay? So as long as the size of x, if the magnitude of x is bigger than 1, then this expression, when you square it, because whether it's positive or negative, it'll end up at the same number, positive something. So as long as x squared ends up greater than 1, that's how we say it, right? Absolute value of x is greater than 1. And f double prime of x is less than 0 means that x squared minus 1 is less than 0 means everything else, right? And everything else will be that the absolute value of x is less than 1. So in other words, when you square x, you need a number smaller than 1 such that when you subtract 1 from it, you get a negative, right? Which will be then less than 0. So that would meet the requirements, right? I mean, these have to kind of be opposite of each other. Right? They can't be overlap. It can't be both positive and negative. So what does all this mean? The curve is concave up. From negative infinity to negative 1, and from 1 to infinity. Okay, that's where x is greater than 1. That's where the absolute value of x is greater than 1, right? And it's concave down. On the interval from negative 1 to 1. Okay, and if we look back at the domain, those are our three pieces of the domain, right? I think, yes, they are. Those are our three pieces of the domain. There's no point of inflection because you can't make this 0. Right? So no point of inflection. Or normally you'd say, oh, hey, you got a point of inflection here because you're changing concave up to concave down, right? But we don't because we're not defined at negative 1, right? Since no point of inflection, since 1 and negative 1 are not part of the domain. Okay, curve's not defined there, not part of the domain. Otherwise, you say, hey, you're changing from concave up to concave down. There should be a point of inflection at negative 1, but negative 1 is not part of the domain, right? So there is no point of inflection. And that leads to the last thing, right, which is H, which is sketch. Okay, so H, sketch. Okay, so we put in our asymptotes, right? This is y equals 2. This is x equals 1. This is x equals negative 1. We already know that this is going on, right? And we know that this is concave up and decreasing. This is concave up and increasing. And this is concave down, has a local maximum at 0, 0. Is increasing from negative 1 to 0 and decreasing from 0 to 1. So It's kind of almost like a checklist, right? You can go through this from left to right and say, well, from negative infinity to negative 1, it's increasing, right? So somewhere in what you've written, you should be saying from negative infinity to negative 1, it's increasing. From negative infinity to negative 1, it's concave up. Somewhere in there, in what we wrote, it should say concave up. From negative 1 to 0, it's increasing and concave down. From 0 to 1, it's concave down and decreasing. And from 1 to infinity, it's concave up and decreasing, right? So all of that matches up. Right? And that's kind of the way you're going to sketch the thing on the assignment, which is still due on Friday. Okay, that's one. One more. So of the 12 questions in the book, some of them are like this, right? They're radical. It's a radical. Right, so that's why I'm doing Tuesday. I'm not doing a polynomial. Those are pretty straightforward, okay? You're capable of that. All right, so again, we're going to follow, right? So you just need to follow some method that gets you everything. And the method in the book, right? A, B, C, D, E, F, G, H, domain, intercept, symmetry, blah, blah, blah. If you do enough of them, you should have it figured out. Okay, so A, domain. Okay, anything not in the domain here? Well, x plus 1 has to be greater than or equal to 0, right? No, it can't be equal to 0, right? Because then you'd be dividing by 0. So x plus 1 has to be greater than 0. Because you cannot take the square root of a negative, and we cannot have the value 0. Which means, what does that translate to, right? It just says that x is greater than negative 1. Or, saying it more precisely, I like this a lot better. Then I don't have to watch people butcher the less than and greater than signs, right? It's just there. There it is, right? We can all read this. Okay, so we're from negative 1 up to infinity. That's our domain. That's kind of important, right? Because when we start looking at other values and you're saying, hey, the first derivative is 0, yeah, no, it's not, because that's not part of the domain, right? So keep this in mind. Because when we start finding values and saying, hey, the first derivative is 0 at negative 12, no, it's not. We don't have that. It's not part of the domain of this function. Okay, B, intercepts. What does that matter? I gotta turn off email. I don't need any embarrassing emails. Intercept, so the Y-intercept. You set x to 0. We get 0, 0, right? 0 divided by 1, which is 0. And so that's our intercepts, right? Symmetry. Oh, right. And you notice the symmetry here, right? It's like this, reflected. So all I had to draw was that. I find it and I just never tend to use it. Okay, so to determine symmetry, you do f of negative x. If f of negative x is equal to f of x, it's even symmetry, it's a reflection about y. If f of negative x is equal to the negative of f of x, then it's odd symmetry, and otherwise there's no symmetry. This is not symmetric, right? I mean, that's the same as the original, and this is different, and yeah. So, no symmetry. Asymptotes. wait, I should write asymptotes. The horizontal asymptote, if there is one, limit as x approaches infinity. I'm not doing negative infinity because it only goes one way, right? So it's not plus or minus infinity. There is no negative infinity. It's not in the domain. Of x squared over the root of x plus 1 equals, well, it's going to be really big, and so is, this will be somewhat smaller, so it's just going to be infinity. So there's no horizontal asymptote. Okay, no horizontal asymptote. Okay, because this doesn't go to 0, right? It just gets big, but not quite as big as that gets big. Good. Okay, how can we make this 0? We can make this 0 by going to -1, right? Closer that we get to -1, this gets closer to 0, which means there is a vertical asymptote. Okay, so as x approaches -1 from above, okay, can't go from below. So f of x is always positive. Right? You're squaring a square root. The square root is positive by definition, right? The principal or positive square root. X squared is always positive. So that means the limit as x approaches -1 from above of x squared over the root of x plus 1 is equal to infinity. So we have a vertical asymptote, right? So x equals -1 is a vertical asymptote. Right? So we got our asymptotes. Now we can kind of sketch something out at this point, but there's no real point, I guess, at this point. Okay. Now the fun stuff, right? Derivatives, yay. E. So intervals of increase or decrease. Wow, how did I do that? It's okay, I fixed it. Okay, so what do we got? Fun stuff, right? What was the original? So it's the denominator times the derivative of the numerator. So I'm going to do the derivative of the numerator first. 2x root x plus 1. Right? It's less awkward than writing root x plus 1 times 2x. Minus x squared times 1/2 x plus 1 to the -1/2 times 1. I'm not going to put that in, right? Because that derivative of x is 1. Over x plus 1, right? Because it's the square root of x plus 1 squared, which is just x plus 1.
Don't you have the quotient roll backwards?
Do I have it backwards?
Because don't you go...
No, you just flipped.
Gosh, I hope not. No,
Oh,
yeah,
I mean, you just
I wrote 2x times root x plus 1 instead of writing root x plus 1 times 2x.
Okay, I get it.
So I just said, it's a bit less awkward, because otherwise then I got to put brackets around everything, right? So, yeah, it's confusing but less awkward. All right, so we are going to take out the smallest number. We're going to take out 1/2, right, as a number. And we're going to take out the x plus 1 to the -1/2. Okay, so that's going to be our common, and they have an x in common as well. So I'm going to take out a 1/2, an x, and a x plus 1 to the -1/2. Okay, so to get 2x, I'm going to have to multiply 1/2 times 4, right? I want to get 2x, so 2 divided by 1/2, so 4. And this is going to be an x plus 1, right? So I got x plus 1 to the -1/2 times x plus 1 to the 1 gives me the x plus 1 to the half, or the root. Minus, I already took out the half, and I took out one of these x's, so that's just going to be minus an x. And this will be an x plus 1. Now, what we'll do is put stuff where it belongs, right? So this is going to come down here and make that a 3/2, right?
One sec. How, on the square bracket part, how's this just minus x on minus x squared?
Okay, so there's an x out here,
The x
right?
out
From
there.
there, yeah.
Sorry.
No, hey, trust me. When I'm working through the example, it takes me like 5 times. Like, what? Wait, what am I taking out here, right? You know, it's because you want to take out the half, right? You want to take out the lowest number and the lowest power and the lowest exponent of x. Equals. Okay, so up front, we're going to have the x. In here, we're going to have 4x plus 4 minus x. Down here, we're going to put the 2. And we're going to move this down here, so that'll be x plus 1 to the 3/2. Okay. And it's going to end up being an x. We've got 3x plus 4, so we got an x and a 3x plus 4. And a 2, and an x plus 1 to the 3/2. And you kind of want this, right? I want factored forms. We say, hey, it'll be 0 when x is 0 or x is negative 4/3, which is actually outside of the domain, right? Remember, the domain is negative 1, so the 0 of this doesn't come into play. Okay, so then we say, well, you can't make the denominator 0. You can't have that anyway. So, and negative 1 isn't in the domain. So f prime of x is equal to 0 when x equals 0 and also negative 4/3. And let's state that. Say, hey, I know negative 4/3 is also a 0 of this, but it's not in the domain of the function, right? Because the function is negative 1 up. Negative 4/3 is smaller than negative 1, right? So we're only interested, we have a critical number when x is equal to 0, right? So the only critical number, so let's say that. So the only critical number is x is equal to 0. And then f prime of x, so that will be negative when x is between negative 1 and 0. So f prime of x will be less than 0 when x, basically when x is negative, right? I mean, the 4 here is going to overwhelm this and turn that into a positive. This is always positive down here, right? Because you're taking a square root, which has to be positive, and then cubing it, that's going to be positive. Okay, so it's only when this guy is negative. That'll be between negative 1 and 0. And f prime of x will be greater than 0 when x is greater than 0. Okay, so when x is positive, that's positive, that's positive, that's always positive. So what do we got? F will be decreasing negative 1, 0, and f will be increasing from 0 to infinity. And f prime of 0 is defined, right? It's equal to 0. So we've got decreasing and then increasing, right? Looks like this, giving us a local minimum, right? Minimum. Decreasing to increasing, local minimum. All right, so that's part F, right? F. Since f prime equals 0 and f prime changes from negative to positive. At 0, f of 0, which is equal to 0, is a local minimum, right? And actually, as it turns out, it's also an absolute minimum.
How do you know that at the first point?
Because it's going to infinity and beyond. So we said as the horizontal, as x approaches positive infinity, there's no horizontal asymptote, it's going to infinity. Okay. So we know that it's going up. So it's kind of dipping and then going. By the first derivative test. I always feel sorry for the second derivative test because I don't need to do that because I've already figured out what it is because of the first derivative test. So yeah, and we get to do all this work to find the second derivative because we need our concavity, right? So that's generally what the second derivative is used for. So the second derivative. Actually, G would be concavity, right? Also your inflection points, right? Okay, so it's the okay, what do we want to say at this point? It's the denominator, okay, 2 times x plus 1 to the 3 halves, times the derivative of the numerator. Now, at this point, you need to put the x in, right? Remember we had x bracket 3x plus 4. So we now need to go 3x squared plus 4x and do the derivative, which will be 6x plus 4. Okay, so that's where the 6x plus 4. You got to now multiply it in and get 3x squared plus 4. Minus, and now you got the 3x squared plus 4, times the derivative of the denominator, plus 4x, right? It's good. You're earning your keep. Which is 3. And we got down 4. Okay, when you square 3 halves, you get a 3. Okay, so we factor out an x plus 1 to the half. And we're left with a 2 times an x plus 1 times a 6x plus 4. Okay, because that'll just be a 1 half and a 1. That'll give me my 3 halves. And the 6x plus 4. Minus a 3 times a 3x squared plus 4x. All over 4x plus 1 cubed. So now we can, this will go down here, right? So we're going to have, we got 3 minus 1 half, so that'll be 6 halves minus a half. This is going to turn into a 5 halves down here. So equals, so let's do this first. 4x plus 1 to the 5 halves. Okay, that's that 3, which is 6 halves minus a half. And here, we're expanding this out, so we've got 6x squared, which we'll call 12x squared, plus 4x plus 6x is 10x, and then the 2, so plus 20x plus 4, which is 8. minus 9x squared minus 12x. Okay, which gives me 12 minus 9 is 3x squared plus 8x plus 8 over 4 bracket x plus 1 to the 5x. Okay, so now we need to think about this. So we know our domain says we're from -1 up, right? Not including -1. So this is always going to be positive, right? Because it has to be. I got to square root it. So this will be positive. I'm square rooting it. It's positive. I'm fifthing it. It's positive. Multiplying by 4. So the denominator is always positive, right? So we need to worry about this. And what does it turn out? So let's do this. Since x is greater than -1, the denominator is always positive. So that leaves us to wonder about 3x squared plus 8x plus 8, right? What does that look like? And we can't graph it. But we do have ways. And so I'm going to say this. The numerator is always positive. And you'll say, how do you know? Here's how we know. Since okay, let's look at b squared minus 4ac, right? B squared minus, if you were going to solve 3x squared plus 8x plus 8, which you can't factor, right? So if you're going to solve it for x's, what are the zeros? Part of that is we'd use the quadratic formula, but before we get that far, if we look at the discriminant, we get 8 squared minus 4 times 3 times 8, which is 64 minus 96, which is -32. If the discriminant is negative, there are no real roots, right?
Where did you get that b squared minus 4? Is that from the quadratic?
Yeah, pull it out of the quadratic formula. So remember, it's called the discriminant. Now you got to think back to 20-1. So the nature of the roots, right? So we're looking at this. I've got this quadratic, 3x squared plus 8x plus 8. I cannot just plug it into my calculator and say, oh, look, it looks like, it looks like this. So we could do the b squared minus 4ac and say, look, the discriminant is negative. That tells me I've either got this or I've got this. Except it's positive 3x squared, so it opens up, right? So we're looking at something that looks like this. It means it's always positive, right? There are no negative values. So the second derivative will always be positive, meaning the graph is always concave up. Okay, so let's say a little bit about this then. Since 3x squared plus 8x plus 8 opens up, it is always positive. Okay, so discriminant tells you there are no roots, right? And no roots means it opens up and it's above the axis, or it opens down and it's below the axis. In this case, 3x squared, that opens up, right? Positive x squared opens up, and therefore it's above the axis, so it's always positive. Which means, so we can then say that f double prime, the second derivative, is greater than 0 for all x in the domain, which says that f is concave upwards, is concave up on the domain, right? -1 to infinity, and there's no point of inflection. Because to get a point of inflection, you need to change from concave up to concave down, or vice versa, right? And be continuous at that point, right? Because the other example, we changed concave up to concave down, but it was at the asymptote. So we can graph this. Oh, wait, one second. Or can I just squish it? I can squish it. So we say we have a vertical asymptote at x equals -1, that it's going to infinity there, that it's coming down. There is an intercept, right? The intercept was at 0, 0. Right, is that back further? That's the right one. It's further.
Yeah, it was at 0, 0.
Yeah, okay, so we got an intercept of 0, 0. Also was a local and absolute minimum, right? Somewhere we said that. Yeah, local, and turns out to be an absolute minimum, right? Which we can now figure out. So it comes down to here, and then goes up. And it's concave up the whole time, right? Concave up. Decreasing on the interval, -1 to 0, increasing on the interval 0 to infinity. And that matches up with all the stuff.